Right, so today for the first session of the new year, we're very happy to have Matthew and Jarek to come present at our reading group. Thank you very much, guys, for joining us. I'll give a short intro to the speakers and let them present their work. So Matthew is a graduating PhD student in the FLAIR and Wheel labs at Oxford, interested in video world models and RL as a path to general purpose robotics. He has worked on the Genie team at Google DeepMind and the Gaia team at Wave, as well as publishing research in diffusion, video models, and offline and meta-RL. Jarek Liesen is a second-year PhD student in the FLAIR group at Oxford, focusing on scalable reinforcement learning. And he is the author of ReJAX, a hardware-accelerated reinforcement learning library in pure JAX, and a co-author of a clean state for offline reinforcement learning, which will be presented today at the reading group. This work introduces rigorous evaluation protocols and the Unifloral offline RL library. Thanks again for coming, guys. We're looking forward to the presentation, and it's all yours now.
Cool. Thank you so much. First of all, thank you loads for the invite. Sam and Caleb. This is a really cool group. And I mean, I've watched a few of the videos before, so very grateful for the opportunity to talk to you all. And also, before I start, thanks a lot to Oliad, who isn't with us today, and Jarek. This started as quite a small project, as in we'd worked in offline RL before, and I kind of wanted to re-implement some algorithms in JAX and just make them a bit faster. And slowly we had that classic case of scope creep where you keep wanting to do more and more. And when you have someone like Jacobs as supervisor, there's always a new idea. Effectively just kept going with it for a year and a half and ended up with all of this. So very grateful to them. Today I want to talk about why we care about offline RL, even though it's kind of seemingly got a bit less attention than maybe it once had. Why we think it kind of fell out of fame at one point, and then I guess how we think that the work we're going to present makes it really easy to do novel, impactful research in the space. So we think that with this library we're going to present and the evaluation protocol, it's really never been easier to sort of publish papers and really prove out ideas. So fundamentally, I sort of want to make three claims. The first one being that offline RL is still incredibly important, especially for embodied AI and robotics. The second one being that despite having sort of 7 good years of research in the field, it's still very far from being solved, and there's a bunch of questions still to be answered. And then the third point is that because of the work we're going to present today, it's sort of easier than ever to do research in this space. Is everything all right, Sam?
Sorry to interrupt. I think we're still on the title slide. Just wanted to make sure it's...
Oh, yeah. So, I was just doing a bit of a slow intro.
I was thinking maybe you're just doing the title, but why don't you check? I think we're still on the... okay, all good. Sorry.
Is that all good now?
Yeah.
Okay, sweet. I'll keep going. Cool, So, as I sort of mentioned, most people here today, even though this is a reinforcement learning group, probably haven't focused on offline RL or even thought about it for the past 4 or 5 years. And we think that's quite understandable because the sort of past half a decade has been dominated by scaling up large supervised learning recipes. So scaling up in vision or language, and then taking the priors from those models and using them to quickly learn new policies. And so most of the big capability leaps we've had in sort of policy learning have come from taking these models that are just really good, almost like world models or predictors, have just learned really rich features and applying sort of the same old RL methods on top of them. And so we haven't really seen breakthroughs come from offline RL over this period. So the question is kind of like this tweet would suggest, do we just not need it anymore? Was it kind of a method that had its phase and now better methods have come along? And so to answer that question, we think it's more helpful to think of offline RL as a set of, not so much as a set of methods, but more as like a whole problem setting. And at a high level, that's when you have a data set of experience and no environment access or very limited, and you want to find an optimal policy. And so roughly that happens when you meet these two conditions. One is that you have a large data set of non-expert experience, and it needs to be non-expert because if it was expert, you just behavior clone it. Like you could just supervise learn the actions. And then the second condition is that you need limited environment interactions. And these two conditions are still incredibly common. Like the core offline RL problem setting is super common, especially in embodied AI, where if you think of something like robotic manipulation, your data is going to be quite limited because each one of your teleop setups or your robots that maybe you deploy autonomously is ultimately collecting data in real time. So like you're limited by the number of these very expensive and often quite flaky setups you can build. But then at the same time, the data you collect is going to be really far from optimal because teleoperation, I don't know if you ever use a setup, but is super janky. Like even the really nice ones, the gloves where you get some tactile feedback, it's like trying to solve quite delicate manipulation tasks while wearing oven gloves. So if this problem setting is so important and like so common, and we've had all this research in offline RL, then the question is, why hasn't it given us these breakthroughs? And we believe that comes down to how people have approached these papers and how they've evaluated their methods. So if you read an existing offline RL paper, it's probably going to have two kinds of tables. One of them is going to be a large table of final performance on different data sets, where you look at a bunch of different methods in the past, and you look at a load of data sets, usually from D4RL, and you compare the final performance of an agent after 1,000,000 time steps. And maybe you'll repeat this over 3 to 5 seeds. And then alongside that, you'll have dataset specific hyperparameters for every method you run on. And when you look at evaluations like this, a couple of things are quickly apparent. One is that there's no clear state of the art. So even if you look at this table here, which I think comes from the Rebrack paper, the best method on each dataset varies wildly. So unless you're literally running on that dataset, it's not like online RL where you can probably take PPO and do fine. Like it's really not obvious which method you should use. And if you talk to people in industry using this, like I was at Wave before this, and they're applying offline RL. They had to try multiple different methods because there is no consensus from the literature which the best is. And at the same time, you see that it's not just that different methods tune differently, but the range of hyperparameters they use varies massively between different methods. So you have some methods that are really strict and will only use one set of hyperparameters everywhere. And so that means they're kind of truly sort of zero shot, like they don't tune online at all. And then you have other methods, kind of like LBSAC here or EDAC, which have a different specific combination of hyperparameters on every dataset they train on. Like here you can see LBSAC uses layer norm when you're in hopper medium or ant medium, but only in those cases. And if you're able to tune your model down to that level, the question is like, are you really offline? Or more to the point, if you're comparing to a method like IQL that only uses one set of hyperparameters, are they even in the same problem setting? Like, how do we compare these two? And so if you're a practitioner right now and you wanted to deploy a method, you'd probably have to gamble. Like maybe you'd want to play it safe and pick IQL because you have a good estimate of how it's going to perform generally, on this one set of hyperparameters. But then you're kind of neglecting all these other features that have been proposed since, and a lot of them are probably going to be really good. And at the same time, maybe you decide that you like EDAC, and EDAC does get really good performance on a lot of data sets and beats other methods. But you have no idea how well it's going to do if it's not tuned to the same level of precision that it was tuned to here. And so if you pick EDAC and then you spend 10 million in compute tuning it and you just don't quite get there, you really don't have a sense for how well it's going to perform. So we ultimately think that this is why offline RL has kind of fallen out of favor. It's not that the problem setting is any less important, or that these methods aren't effective at optimizing policies. It's that the field kind of failed to thoroughly define the problem it was trying to solve before it proposed solutions to that problem. And so for the rest of this talk, we're going to talk about how we attempted to ultimately define what offline RL is and turn it into an area of research you can do kind of like impactful and meaningful experiments in. And so I guess the first question, which probably should have started with, is like, what is offline RL fundamentally? And we think that it's less one problem and more a spectrum of problems. So in its purest sense, you have a data set of experience and you have absolutely zero environment access. And then what you care about in this case is the average performance of a policy immediately after training on the data set. And here you've got no signal with which to tune your hyperparameters. So this is kind of the zero shot setting, like the purest setting of offline RL. And we show that on kind of the far left-hand side of this curve. On the other side, you have your sort of fully tuned version of offline RL, where you can train a load of different policies with different hyperparameter settings across your space, evaluate them all to some really high level of confidence in your environment, and then pick the best policy. And what you care about in that case is the true return of the best policy in your set. All you're trying to do is maximize the maximum over the space of policies you can train. And the fact is that in many cases, you lie somewhere on this curve. Like, it's not very common that you're in the purest kind of zero shot version of offline RL, where you've got absolutely no ability to interact with your environment. Like, if you're really trying to train one of these models and deploy it to a customer or some business application, you're probably not going to train it on a data set and not test it at all and just drop it straight out in the world and hope that it behaves. Like, you're going to have some ability to test. If you imagine you're training a robot, you probably have a lab and you're probably using that lab to do the data collection in the first place. So it's not going to be infinite. You're never going to get perfect performance estimates, but you're going to have some sense of how well these policies perform. So what we suggest is that in reality, we don't just care about one of these numbers like we measure right now. We care about performance across this whole spectrum. And if you did measure performance across that whole spectrum, you'd expect to rank methods differently. So if you had a method like this blue one, you'd probably want to select it in the zero shot setting because maybe it has a smaller hyperparameter space, or it's just generally more robust than the red method. However, if you knew you were able to tune, you'd probably want to move to this red one that had a higher performance ceiling. And so to actually generate data that looked like this, we designed an evaluation protocol. This basically has two stages. In the first one, you train a bunch of policies to simulate tuning over. And to do that, you quite simply sample hyperparameters from the range your method specifies. You train on the offline data set, and then you evaluate a bunch of times. And here we don't just record the mean performance, but we record the performance on every individual episode that you evaluate on. Following this, we repeatedly simulate this tuning procedure as if a human was performing it over a set of policies. And to do that, we take these results from the policies we've trained. We pick a subset of the policies, imagining that these were kind of the ones we trained in this particular run. And we use a bandit to simulate tuning. that's trying to basically find the right arm. For this, we use UCB because it's generally pretty robust. And what we measure here isn't the final return, but is the performance of the arm that the bandit believes is the best at each point in time. So what we do is we imagine that we stopped tuning at every step, and we say, right now, which policy would you pick? And if you pick that policy, what would your true return be? And so that's quite a lot. That's a bit complicated, but just to see how this looks, as the first example we ran, you get results that look like this. And immediately it should be kind of apparent why you'd want to use an evaluation like this. If you had no budget to tune, like if you knew that you really didn't have this lab where you could evaluate policies, this shows that you would probably want to go with IQL, because IQL does very well in that setting. Like it's incredibly robust across all its hyperparameter settings. Whereas if you knew you had a lot of ability to tune and you could really find the best policy in your space, maybe you'd want to use SAC-N instead, because that has like a much higher performance ceiling. As a little aside, just to really drive this point home, we noticed that some of these curves had little bumps in them, which is pretty unusual for bandits. Like only certain distributions should generate this behavior. Because usually you'd expect that a bandit that's gathering information to make better decisions should generally make a better aggregate decision, like should be able to pick a better arm on average as it's gathered more data, as it's pulled more arms. But what we show here is that there is a period where sampling more episodes from these policies makes you make a worse decision about the policies before you get better. And surprisingly, this isn't actually a bug. We see that these kind of bumps happen on a bunch of different data sets from certain methods. So this is all rebrac trained on 4 different data sets. And if we pick one of these data sets, I think this might be Walker, and we train, in this case, 100 policies. Yeah, right. We train 100 policies. And then we rank the sort of performance of those policies. We can see quite an interesting distribution. So, sorry, what we're showing on the right here is the mean return of different policies trained by rebrac on this data set, as well as the minimum and maximum return those policies achieve. And if you look closely, this really helps if you see the paper. But there's this large region, almost like the majority of policies, that get a worse mean return than the best policies, so are absolutely suboptimal on average, but actually achieve a slightly higher maximum return than the optimal policies do, and do so quite consistently. Like most of the policies in this region have a higher max than the optimal policies do. And you can kind of imagine when this would be the case. Like in Walker, maybe you've learned a certain gait that means that sometimes your policy starts running and then starts sprinting and absolutely bombs off. But a lot of the time it just falls on its face. And that really pulls down your mean return. Whereas maybe the optimal policies have learned like a light jog, and that means they have a good mean return, but also the performance distribution is quite bounded. And we think this does have a point. This kind of highlights a couple of things. First of all, that you really need to measure the tuning budget, because maybe certain methods are much more likely to generate a distribution of policies like this than other methods. And you don't see that unless you evaluate against the tuning budget. But as well as this, this kind of shows that to do experiments in offline RL, you really have to train a huge number of policies. Like it's not enough to do the kind of 3 to 5 seeds that people did in the past. And with previous implementations, this just sort of wouldn't have been feasible. Like it usually took somewhere between a day and a week to train a policy. So something we did, which Jarek is now going to talk about, was reimplement an entire suite of sort of state-of-the-art algorithms all in end-to-end checks. So I'll hand over to Jarek.
Yes, thank you, Matt. Yeah, so one thing we published with our paper is the Unifloral offline RL library. We implemented a bunch of algorithms, both model-free and model-based, in JAX, which means they're GPU accelerated, so we can train super quickly, which allows us to run these seeds on hundreds of experiments. All of them are single file, inspired by clean RL or clean offline RL, which is called call. And we have a minimal file diff, which means implementations are very easy to compare. So now I will dive a little bit deeper into these 3 points and give you a little bit of an advertisement about this library. Then, I will show you our final results, a big evaluation of all these methods, and then I have a little bonus for you. So, as Matt said, other libraries, they take a long time to train policies compared to ours. So this is just a little plot which shows you the total training time, or the sum of training times to train one policy using every single model-free offline RL algorithm. So we do this in just under an hour, whereas offline RL kit and call, these two are like our two main baselines, they take up to 10. So call, they also have a version JAX call, which is still slower than Unifloral, but we unfortunately couldn't include as a baseline here because it's not as comprehensive. They only have a limited set of algorithms. So now you can train these policies in minutes, which is really nice. Next. We also have single file implementations. As you see, our whole implementation of SecN fits onto this one slide and is in just under 400 lines. Whereas call, which is a clean RL style library, is significantly longer because implementations in call, they often have additional features that are not kind of a core part of the algorithm design. Whereas in Unifloral, our files do not contain anything that isn't specified in a paper that introduces a new algorithm. So you can be really sure that everything that corresponds to the performance, or that contributes to the performance you see in the end, is in this file. Okay, next. While implementing all of these methods, we realized they have like a pretty clear ancestry structure. So we were thinking a little bit about method design, where new offline RL methods usually build on some kind of parent by adding a new feature. For example, behavioral cloning is one kind of base method, BC, and TD3BC adds some kind of auxiliary terms to BC and learns a value function. So the existing implementations, they, despite this kind of clear structure, varied wildly, because an implementation of behavioral cloning would be like pretty independent of the one of TD3BC. So if the algorithms are so compositional, why shouldn't the implementations be? This is exactly what we did by only changing a minimal number of lines to get from one method to its child. So here you see SecN, EDAC, and CQL. And these kinds of screenshots are literally the whole file diff. So before, if you wanted to understand how two methods differ, you had to read like pages of mathematical equations. Now you don't even have to read an entire implementation. You can just look at a file diff. So here, this is the 3 whole implementations, just in red and green, showing the file diff, where on the left, it's just the additional hyperparameters, and on the right, it's just the changes to each loss function. Okay, next. So given our new evaluation method and this super fast library, we can take another look at the field and all of the state-of-the-art kind of algorithms. We ran a massive evaluations over thousands of policies, over most of what D4RL has in store, which looks a little bit overwhelming with all these lines, but let me point out some trends to you. So rebrec and IQL consistently perform well across datasets. IQL, which is here in brown, is specifically good in the 0-shot setting, or in other words, it's pretty robust to hyperparameter settings, whereas rebrec tends to have the highest performance ceiling. Also, some other methods that previously were thought to perform pretty well are actually not as good with a limited kind of online budget. So if you're a practitioner, this gives you a pretty clear idea of which algorithm to use given your specific constraints. But if you're a researcher, this might not be enough for you, and you might not only want to evaluate existing algorithms, but you want to invent the next new algorithm. We thought about how can we make this easy, and to do this, we took another look at our algorithm taxonomy and realized most of these algorithms have a shared backbone, and BC and SecN are pretty compatible. So it might be possible to look at the union of all of these extensions that these algorithms have made to their parents. So what would happen if we combined all of these into a single algorithm and do what Rainbow has done for online RL to offline RL? And we get to the Unifloral algorithm. This combines every single component from these standard methods into a single implementation and a single hyperparameter space. And throughout all this, we made a serious effort to keep this minimal, fast, and as clean as possible with no unnecessary fluff. Okay, so now every one of these methods is just a hyperparameter setting of the Unifloral algorithm. So if you want to compare 2 different algorithms, you don't now even need to look at the file diff. You can just look at the difference in hyperparameters. You can just compare the config files. For example, this is behavioral cloning as an instance of Unifloral. If instead we want to train TD3BC, we just change parameters around a little bit to give the TD3 terms a non-zero weight. And if we wanted to extend to rebrec, we can just make some more changes, and there we go. So in this space, there's no distinction between an algorithm and its hyperparameters, but they're truly like the same object. So we think that this makes it easier and faster than ever for you to do novel and impactful research. And while most talks would end with this claim, we wanted to prove this claim. So looking back at our results, what if we took the two best methods, IQL and rebrec, and just stuck them together? Both are based on behavior cloning, where IQL has some advantage-weighted regression in its BC term, and rebrec adds some other auxiliary terms. And to combine them, we just need to use, or we can just look at the Unifloral config and combine the two hyperparameter settings, which now gives us a novel algorithm, TD3 AWR. Oh, sorry. So surprisingly, the resulting algorithm is much more consistent than both its parents and combines the best of both worlds. A lot of the consistency of IQL with the high performance ceiling of rebrec. So now it is trivial to push state of the art using our library. So we generated this idea in a few seconds, the code in a few minutes, and we had the results in a few hours. So what would have before taken a whole conference cycle, we did in a weekend. And to prove this wasn't a fluke, we did it again. Looking at the model-based offline RL algorithms, we realized that most of them use SAC to optimize their policy. However, next slide, please. SAC doesn't perform very well at all in our evaluation. So what if in these offline RL, in these model-based methods, we replaced their policy optimizer with rebrec? The resulting method we call mobrec, which is a MoPo world model combined with rebrec. And this significantly improves performance across almost all data sets. So this was next to no effort for us to bring model-based offline RL back up on par with state of the art. I think this is a super cool result, but what if you didn't want to create a new algorithm by combining existing ideas, but to create a truly novel idea?
Cool. Yeah. Yeah. So this is very late breaking, but we sort of wanted to prove something else, so thought we'd add it during the talk. So yeah, what Jarek's just shown is kind of two examples of taking components from prior research and sort of sticking them together in better ways so you can get high return. And that's a perfectly valid mode of research. I think that's probably the majority of research, and that's where a lot of breakthroughs come from. But we didn't want to limit Unifloral to just that. Like, we don't want to suggest that it's only good for taking kind of Lego bricks from previous methods and building new shapes out of them. So we wanted to demonstrate that you can actually add new features in Unifloral very easily. And that's hard to really convince you of, because ultimately it's down to you implementing those additional features on the Unifloral algorithm. But we, like Jarek said, made a serious effort to keep the implementation super minimal and really clean, kind of like excessively so. And that means that it's quite straightforward to kind of plug in new modules or new losses, and much simpler than it would have been to add them to these prior implementations that had a lot of kind of baked-in assumptions about how the method was going to work. And one idea we had to test this, which is something I'm personally a big fan of, is adding world modeling as an auxiliary loss to the policy. So for this, we took TD3 AWR, which was that method we showed earlier. And all we did was add a world modeling head to the policy and added a loss, so that world modeling head tried to predict the next state from any state. And that didn't affect the action at all. All that would do is help the policy learn richer representations and representations that help it predict the next action. Like there's nothing changed in the action objective. And so it's not here, but that took 20 lines of code to implement. It was, I think it added 20 and maybe removed 4. But ultimately, you can implement that with a very minimal change. And then once you've done that, you can now add world modeling as a sort of auxiliary term to any existing offline RL algorithm. So looking at it here against or with TD3 AWR, these are kind of early results, and these aren't in the paper. These are things that we really only did recently. But there are kind of signs of life here, like it's not completely monotonic, like it's not always better. But in things like Hopper and Penn, there's a clear step up in performance just from adding this term that really doesn't affect the action space at all. It's just kind of like coaxing the policy to learn better things. This method in particular is something I believe in, particularly given the sort of space of video modeling right now, and that we have very large scale pre-trained world models. So I think like as an early sign of life, which, I mean, anyone here, if you're interested in this, feel free to take it and like build something serious with this. We think that's a direction that's worth exploring. Cool. Yeah, so now we're all out of results, but thank you very much for listening. We really do think offline RL is one of the most interesting problem areas you can work in, particularly for robotics and embodied AI, which has a load of headroom left. And with Unifloral, it's very simple to work on. So happy to take any questions.